For decades, we had a simple story about the early universe. After the Big Bang, everything should start small, faint, and slow. Then the James Webb Space Telescope looked back in time and found galaxies that seemed too bright, too massive, and too mature. Way too early. So what exactly did Webb see? And does it actually break cosmology, or are we misunderstanding the evidence? In the next 8 minutes, we'll break down the early galaxy problem in plain English, what scientists expected, what Webb observed, and the main explanations researchers are testing right now. To understand the shock, you need one idea: time. When you look far away in space, you're also looking far back in time. Light from very distant galaxies has been traveling toward us for billions of years, so telescopes can see the universe at different ages. The earliest era we care about here is the first few 100 million years after the Big Bang. Back then, the universe should have been a tougher place to build big galaxies. Why? Because galaxies don't appear instantly. They grow by pulling in gas, making stars, and merging with other galaxies. And there's another issue. The earliest light gets stretched by the expansion of the universe. That stretching is called redshift. The higher the redshift, the earlier the object. But high redshift galaxies are also incredibly faint. For years, older telescopes like Hubble could find candidates, but most were tiny smudges. Astronomers expected Webb to find more of them, not to find a crowd of unexpectedly bright ones. Webb is different because it's built for infrared. Infrared matters because the universe stretches early ultraviolet and visible light into infrared by the time it reaches us. So Webb can see what other telescopes struggled to detect. When Webb's first deep field images arrived, they were stunning. But behind the beauty was a scientific surprise. Researchers started identifying galaxies at extremely high redshifts, meaning the galaxies existed when the universe was very young. And some of these galaxies weren't just detectable. They looked strong, bright, and in some estimates, surprisingly massive. That's where the headlines came from. Galaxies that shouldn't exist. But here's the important part. A telescope doesn't directly measure a galaxy's mass. It measures light. Then scientists use models to translate that light into properties like star formation rate, age, dust, and mass. So the controversy isn't just Webb saw a giant galaxy. It's when we interpret the light using our standard assumptions, we get galaxy properties that feel uncomfortably extreme for that era. Before we get to the explanations, let's ground this in what astronomers actually do after a deep field drops. They don't just stare at the picture. They run catalogs, measure brightness in different filters, estimate redshifts, and then fight with the models. And Webb's early results came from multiple programs, meaning the pattern wasn't just one team seeing one weird thing. Some surveys focused on wide areas to find rare, bright objects. Others went ultra-deep on tiny patches of sky to dig out the faintest galaxies possible. What kept raising eyebrows was a simple pattern. When researchers converted Webb's infrared light into estimated masses, a few candidates looked like they had already built an astonishing amount of stars. Not just a little earlier than expected. More like, if this is correct, the universe was assembling big systems at full speed almost immediately. That's why the debate got so intense, because if even a small fraction of these objects hold up under spectroscopy, it changes how we model the first billion years. Explanation 1. Some of the galaxies might be closer than they look. Early on, many candidates were selected using photometric redshifts. That's a method where you estimate distance based on how the object's brightness changes across filters. It's powerful, but it's not perfect. The gold standard is spectroscopy. Spectroscopy looks for specific fingerprints of elements and molecules and measures how much those fingerprints are shifted. When spectroscopy confirms a galaxy is truly at a very high redshift, that's when the case becomes much stronger. Explanation 2. The galaxies might not be as massive as the early estimates. A galaxy can look bright for reasons that don't require extreme mass. For example, if it has a burst of star formation, or if its stars are unusually efficient at producing light. Explanation 3. Dust can fool you. Dust doesn't just dim light, it reshapes a galaxy's colors. If you assume the wrong dust properties, your mass estimates can swing. Explanation 4. Gravitational lensing. Sometimes a massive object between us and a distant galaxy bends space-time and magnifies the background galaxy. That can make something look brighter than it really is. Lensing is real, and it's common in deep field images, but it doesn't explain everything. And explanation 5. Maybe the early universe formed stars faster than we thought. Not a total rewrite of physics, but a revision of how efficiently gas turned into stars and how quickly early galaxies assembled. This is where the story gets interesting. Because even if the most extreme early claims get revised downward, Webb still appears to be revealing a universe that matured fast. So does this break the Big Bang model? Not automatically. Modern cosmology has room for surprises. Science doesn't collapse when data doesn't match expectations. It adapts by checking measurements, improving models, and testing new explanations. The real Webb story isn't just that it takes pretty pictures. It's that it forces our assumptions into the open. How do we convert light into mass? How do we handle dust? How confident are our redshifts? What biases appear in the brightest objects we can detect first? Over the next few years, more spectroscopy, deeper surveys, and better modeling will tell us which early galaxies were misidentified, and which ones are genuinely surprising. So here's the question to keep in your head. If the early universe built big galaxies faster than expected, what else did it build that we haven't even learned how to recognize yet? This is Cosmic Enigma, and the deeper Webb looks, the stranger the universe gets. First, spectroscopy. If a candidate really is at a redshift of 10 or 12, spectroscopy can confirm it by locking on to specific lines, like Lyman alpha or other strong emission features, and measuring the exact shift. Second, deeper imaging. If a galaxy is only bright because of lensing, deeper observations can reveal the foreground lensing structure and the distorted arcs that give it away. Third, better models. Early stars may not look like stars today. If the first stellar populations were hotter, more massive, and short-lived, they could produce a lot of light without requiring the galaxy to be insanely massive. And here's the part most people miss. Even if the universe isn't broken, Webb is still rewriting the timeline of when the first complex systems appeared. The first billion years may have been more efficient, more chaotic, and more productive than we expected. So if you take one lesson from this, when you hear galaxies that shouldn't exist, translate it to the real scientific question. Which assumption is wrong? The distance, the dust, the lensing, or our model of early star formation? Because that's how progress happens. Not by defending a theory, but by finding exactly where it stops matching reality. Quick recap. Webb didn't prove the universe is wrong. It revealed a tension between what we expected to see at extreme distances and what the infrared data seems to suggest. Some candidates will move closer once spectroscopy locks in the redshift. Some will shrink once dust and stellar models improve. And some may remain genuinely surprising. Either way, this is exactly what a new telescope is supposed to do. It doesn't just add details, it forces new questions. This is Cosmic Enigma. And if Webb is already challenging our timeline this early, imagine what the next deep surveys will uncover.